Good day to everyone, and I'm very pleased today to have one of the pioneers and leading figures in the field of mathematical epidemiology with us today, Glenn Webb from Vanderbilt University. Glenn is a fellow of the American Mathematical Society. He is a constant visitor and speaker and organizer of activities at the Fields Institute. And Glenn is also an honorable member of our Center for Disease Modeling since the SARS pandemic. And there are lots of interactions. We have been very fortunate to be able to interact with Glenn. And today he's talking again about something I think is of critical importance for many part of the group, and here's the title, so I'll give the time to Glenn. Thank you again.
Well, thank you very much for your kind introduction, Jian Hong, and I'm very happy to be here at the Fields Institute, and I appreciate everyone who has tuned in to my talk today. I'll try to be informal, and if you have questions at any time, please do ask. I'll be happy to try to answer questions. My subject is the COVID-19 pandemic and a mathematical model of this epidemic that has the capacity to predict and evaluate the impact of vaccination programs. So let's see if I can make this work. Here we go. So here are my objectives. As I said, I want to develop a model of COVID-19. I want to incorporate the features of this model, which are unusual and important in understanding this viral epidemic. One is asymptomatic infectiousness, which is very important because we know that many transmissions are caused by infected people who are asymptomatic. That's very unusual. It happens sometimes in some influenza epidemics. For example, 100 years ago, there was a influenza epidemic called the Spanish flu, and it was terrible. It killed more than 500,000 Americans at that time when we had a much smaller population. And it was estimated that the period of asymptomatic infectiousness was about 1 day, maybe a day and a half or 2 days. But now we know it's much more significant, much longer for COVID-19. We also want to incorporate symptomatic infectiousness because, of course, symptomatic cases are very important in transmitting the disease as well. Another challenge in developing models for COVID is to use the data. And so the data available is typically what we call reported daily case data. And I want to use this data to parameterize the model. And that's difficult because the data, as we see, is typically a mess. And then, as I said, I want to apply these models to issues such as social distancing measures, public health policy, and most important, vaccination programs. Okay, here's my model. It's a standard differential equations, a dynamic model of a infectious disease. We have 4 compartments: the susceptibles, capital S of T, T is time; the asymptomatic infectious population, capital I of T; the reported symptomatic infectious population, capital R of T; and the unreported symptomatic infectious population, capital U of T. Okay, so we have the terrible problem of identifying parameters. This is always a big problem in applying mathematical models to physical and scientific problems. And it's especially true for this model, this epidemic. And so we want to identify a transmission rate. So we'll assume that susceptibles become infected from asymptomatically infectious and symptomatically infectious individuals at a certain rate that depends on a time-dependent parameter, tau of t. the susceptible population at that time, the asymptomatic infectious population at that time, plus the unreported symptomatic infectious population at that time. Notice I don't have the R, capital R of T. So I'm making a simplifying assumptions, and I make many simplifying assumptions. I assume that reported symptomatic cases no longer contribute to transmitting the infection. And that's a debatable assumption, but for the most part, if someone is reported, they are medically confirmed by a medical authority to be infected, and they're typically isolated, and they don't continue to produce infections. They may have caused infections before they report it, but once they report, we'll take them out. That's a simplifying assumption. And we'll have an average period of infectiousness of asymptomatic infectious individuals. That'll be 1 over Greek letter nu days. And later I'll take that to be 7 days. So nu will be 1 over 7. So that's controversial too, because how long is the person asymptomatically infectious? Well, 7 days is on average is not a bad guess, but it would be controversial. I'll assume that reported infectious individuals are infectious, are infected, change that word infectious to infected for 7 days as well. There's a parameter 1 over eta, and eta will be 1 over 7. My time units are days. Time units are days. And so these assumptions arise from the first order loss term in the equations for these compartments. Another important assumption is the fraction of individuals who become reported and the fraction who, 1 minus that fraction who remain unreported. And that again is controversial, but I'll assume that it's 2 to 3, that for every 2 cases reported, there are 3 unreported. And again, it's controversial. Sometimes it's more, sometimes it's less, but these are simplifying assumptions which could be modified if better information is available. So that's the parameter story. Here are the equations. The susceptible population, the susceptible population has its transmission term, which is a loss of individuals who become infected, and that term has this form right here. Remember, tau of t is a function I have to identify as a time-dependent parameter. So this is kind of a mass action form. It depends on the number of susceptibles pounding against the number of infected asymptomatic individuals, infectious individuals, and the unreported symptomatic infected individuals. Then there's a loss term here as well for the susceptible population. It's just minus V of t. And that's the number of people vaccinated each day, but not quite the number of people vaccinated, but the effectiveness of the vaccination for the people vaccinated each day, which is somewhat less, of course. I'll talk more about that. So the susceptible people are lost to the infected asymptomatic infectious class. Here's the diagram. Here's the susceptibles. They become asymptomatically infected or infectious at this certain rate. And then they are lost at a rate, and a certain fraction, which I'll call nu1, go to the symptomatic reported class. The remainder, 1 minus nu1, which I call nu2, go to the symptomatic unreported class. They remain in those classes, this one and this one, for 1 week, then they go to the removed class. And then susceptibles are removed by vaccination. So you become removed from this class by getting infected or by being vaccinated. Okay, so there's the equations. This is a fairly standard SIR model. Okay, now a major problem, as I said, in working with models of COVID-19 is to use data. And the data that we have is daily reported cases. And so let's see, did I skip something here? No, Okay. Okay. Daily reported cases. So how do we account for daily reported cases in the model? Because we want to connect daily reported cases in the model to the daily reported cases data. The data is given to us every day. Every day you can go on the internet and see how many cases were reported yesterday in Canada or the US or the UK. And of course, as I said, that's a fraction. And typically we assume there are more unreported cases daily than reported cases. But in the model, there's a simple way to describe the daily reported cases in the model. It's a function, I'll call it capital DR of time t, daily reported at time t. The change in that dependent variable is equal to the number of cases going into that variable. Let's go back to the equations. You look at the number of individuals going into the reported cases, it's nu 1 times I of t. That's the entry into that class. So that term goes right here. That's the way you get daily reported in the model. And you stay in that class for 1 day. So there's a -1 times that value. So this is the equation that the daily reported cases in the model satisfies. It's simply dr prime of t equals this parameter to nu 1 times I of t minus 1 times dr of t. Remember, time units are days. And so I solved this equation for I of t, and here's the formula for the infected cases at time t in the model. It's simply this expression right here, which is obtained from solving this equation. Okay, so we go back to the equation for I of t in the model. Where was it? It's right here. And so now we take that equation, take a look at that equation, and we write it here. I've just rewritten that same equation right here from the model. I've transposed the term to the other side of the equation. Now we know I of t from this equation, and we assume that the transmission rate satisfies this equation. This is just the equation for I of t in the model, and so this term, we take this term and we solve for it in this equation, and we have this term is equal to I prime of t plus nu I of t. So now we can obtain the expression for the transmission rate in the model, which is given by this term right here, and we really don't know it, but it's equal to I prime of t plus nu I of t. And since I of t is equal to this expression, I hope you can see my cursor, okay? I assume you can see my cursor. I of t is equal to this expression, so we take this expression and we put it right here. We multiply it by nu. And we take the derivative of this expression and we put it right here. So this derivative of I of t goes here, plus nu times I of t itself here. So we have a formula for the transmission in the model. Okay. So now I want to connect the daily reported cases in the model to the daily reported cases in the data. And so we'll see with examples, and you all know well that the daily reported cases of COVID epidemics in varying countries or locations is zigzaggy, jumpy, crazy. It's going crazy very often. It can double from 1 day to the next. And so it's quite difficult to use that very messy data. So we do something that's very well known now, even in the public, the internet reports. We take a rolling weekly average of that daily reported cases data. And the idea is you just take today and you take the average daily reported cases data for the past 7 days, take the average of that, and you replace the value you got today by that average for the past 7 days. And that's called typically the rolling weekly averaged daily data. So we get a value for that each day. And it's much nicer than the daily data. This average rolling data is quite a bit nicer. It's still kind of a mess, but it's much nicer for most examples. So we're going to use that instead of using the daily reported cases data. we're going to use the weekly rolling average daily reported cases data. And so that will be incorporated into the model. So how can we do that? So we take, I'll show you examples, but we take the daily reported average rolling weekly cases each day, and that's a discrete set of points, one each day. There's a point over each day. Today it was something in Canada, yesterday was something else. And so we want to take that data, and that's discrete data, but we want it to be a continuum in our model, because our model is a continuum model. It's based on averages over time. So we want to replace that rolling weekly average data, discrete, with a continuum interpolation of it involving B-splines or cubic spline approximation. I'll show you how we do that. So we take that cubic spline approximation to that discrete data, and we remember our transmission term had this expression in our model for the daily reported cases data in our model. And we take that daily reported cases in the model and replace it by this continuum B-spline, cubic spline interpolation of that discrete data. So here's the formula for our transmission in the model. And so we can solve for this function tau of t. We take this equation, we solve it for tau of t, and it has this formula right here. So now we know the transmission up to the last day of reported data that we can incorporate into our model. That's how we connect data to the parameters in our model. Okay, now I want to go to work and apply this to the United Kingdom. And the data here is from Wikipedia. There's different sources of data. There's WHO, there's Wikipedia, there's various sources. Countries have their own sources. Let's take a background look at the UK as far as COVID-19 goes. Last year ago, February, the first cases arose. In March, the government imposed stay-at-home orders and banned non-essential travel and closed gathering places, so on and so on. And for 3 or 4 months, the cases and deaths slowed considerably. And then at the end of that time, the government relaxed the lockdown restrictions, and the cases remained low for a few more months, but then they resurged quite dramatically in September and October of last year. November 25th, they had the highest number of deaths since the May, almost 700. And end of December, they imposed new restrictions. So that's the background. Okay, so we want to set up our parameters in the model for the UK. As I've said, we'll take the period of asymptomatic infectiousness to be 1 week, 7 days. Likewise, the period of symptomatic infectiousness, 1 week, 7 days. We'll take the fraction of reported symptomatic cases to be 40%. So F will be 0.4. The unreported fraction will be 60%, 0.6. And we'll take the initial population of the United Kingdom to be 68 million approximately. Okay, so here's the data. As I mentioned, the data is quite a mess. So these vertical bars represent the data each day, starting on March 1st, approximately. We'll call that day 1 last year, up to 2 weeks ago, January 15th. So that bar right there is the daily number of reported cases on January 15th, about 50,000. And as I said, it jumps around quite terribly. It's a little bit well behaved here, not completely, and here, but here this is the resurgence that I talked about through September, October, November, and new restrictions caused it to go down, but then it rose again in late December and January. It's going down now in late January. This data is from WHO, and I will update it, as I mentioned, soon, because it's 2 weeks old. That's quite old. So that's the point-wise daily data. Now we want to weekly average that and roll it, so on. And so I took the points at the top of those vertical bars. You could put a point at each top of a vertical bar, and I put a continuum cubic spline through it. And I call that curve BS of t. So that stands for B-spline interpolation of those points, that discrete data. Now I have a continuum curve through the data. And I should say, by the way, this is the points are the rolling weekly average, not the daily. This was the daily average. I roll that, as I've talked about. You know, you've seen these graphs all over the place. And those black dots then are the rolling weekly averaged daily data. They're still discretely presented, one for each day. Then I put the B-spline curve through it, and it's I think the dots are purple and the curve is black. Okay, so that's a job you have to do, and but it's easy, and we get this continuum interpolation, and it's nice and continuous. It goes through those discrete points, the black dots or purple dots. It's continuously differentiable through those dots. It's even twice continuously differentiable through those dots, but it's not 3 times differentiable. The second derivatives are piecewise linear, but they share those dots at the days. Okay, so I take that data and this is the cumulative data. Very often you see the cumulative data, and many times modelers will work with the cumulative data because it's nicer. It's much nicer than the daily data. You see of course, it's always increasing, but it's very well behaved in most regions. We can see trends for sure, but it's easier to approximate this than it is this cumulative rolling, the rolling data, daily data. That's more jumpy, more difficult, but more accurate, somehow more meaningful than this cumulative data. So, but nonetheless, the cumulative data looks like that. Okay, now I want to bring in vaccination. And in the UK, vaccination began in mid-December with a 2-dose Pfizer regime or regimen. And then somewhat later, the National Health Service delayed the second dose, which is supposed to be given a certain number of weeks, I think roughly 3 or 4 after the first dose. And they delayed it to extend the number of people who could be vaccinated. In late December, they approved AstraZeneca, and that is similar, has a similar efficiency, effectiveness, and they again delayed the second dose for that. And beginning in January, they started vaccinating approximately 2 million people per week in the United Kingdom. Here's some references on that. So I want to put that in the model. And it's easy to put vaccination into the model. You just have this function, which I called little v of t. It's known to us. We know how many people are vaccinated, roughly 257,000 per day. That's 2 million divided by 7, beginning January 1st. Now, but we must identify a effectiveness of that vaccination rate, because not every person that gets vaccinated has a successful immunization, and also can take 3 or 4 weeks after that shot. You're not instantaneously immune to infection. It can take up to 3 or more weeks before you become immune to infection. So there are those issues at understanding the way vaccination removes susceptibles from becoming infected. This is the transmission rate right here that we talked about. And this is the loss of susceptibles due to vaccination. So I will take various values for these fractions and look at the outcome of vaccination dependent on this fraction of successful vaccination. Okay, so there's the equations. What's this? This is the model for the UK with the data. What are the things going on here? The vertical bars are the daily reported cases. The purple dots are the average daily reported cases per week, weekly rolling. The blue graph is the model simulation of the daily reported cases data. And so I assumed here that vaccination effectiveness, because it started in 1st of January, and this data goes through January 15th. So it had some little impact the first 2 weeks of January, but very little. but I assume that the efficiency was 90%, was 90%. Okay, so then I take the model with that efficiency assumption and all those parameters, all that information, and I develop the cumulative reported cases, which is just the integral of the number of infected individuals starting at day 0, which is March 7th, and going out to the present days, January 15th, multiplied by nu1, because that's the fraction that go to this reported symptomatic class. Here's the fraction that go to the unreported cumulative class. It's nu2, which is 0.6, times this integral. So I graph C R of t, cumulative reporter, that's the blue graph. I graph C U of t, that's the green graph. The purple dots are the rolling average daily data. This red graph is the number of reported cases at time t, and the purple graph is the number of unreported cases at time t. So the model gives this information up to the present data report date, January 15th. This is January 15th, right here, the last day. It's not quite in agreement here. There's a simple reason for that, but I won't go into it. Okay, so now I want to go forward. I want to go past January 15th. I want to go out months and see how vaccination plays a role. So how do I design the transmission rate? I should look at the time, see how it's going here. Okay, so how do I design the transmission rate? Remember, the transmission rate has this form. And before January 15th, I know what tau of t is. Of course, I know S of t, I of t, and ut, but I know what tau of t is as well. But in fact, the transmission rate has this form, which we identified with this certain story to have this form in our model. So I take that transmission rate, which I have in my model up to January 15th, and I graph it for the past week. So January 15th, I think, is right here. It's day 22. And it's that point right there. And sorry. And the previous day, it was this value here. Then you go back about a week. And so I take those point dots. And remember, in my model, the daily transmission rate goes through those point dots, but it connects them with this B-spline curve. And the formula that you get for the transmission rate each day has this graph right here by that process. And I want to go forward. I want to identify the transmission forward. I could just take the last value here and say it's that with my mass action terms included. But there's so much jumping going on here. It's so irregular that I want to take the linear regression fit to those dots, those 7 or 8 dots for 1 week. And it's at the red graph. So I want to take that as my going forward value. So I identify a time, I call it T sub x, which is the time that we will change from reported cases data information daily to a new form in the model going forward from that date. So I see where this red graph intersects this blue curve. In 1, 2, 3, 4 places, I take the last value where it intersects, and that's 319.3, day 319.3. And I'll take that as my value, and I'll call it tau of tx, S of tx, I of tx, U of tx. Okay, so this is my transmission for the model going forward. The 4-time tx from March 7th, T0 to what did I say, January, whatever it was, 317.3. It has this formula here, as I talked about earlier. Forward from tx, it has this formula right here. So I just take this formula and I multiply it by this ratio right here. And so at time tx, this ratio right here is 1. So at time tx, these match. But going forward, this one takes over. And this now involves the susceptible population at time t and the I of t and the U of t populations at time t. So this brings in the dynamics of the loss of susceptibles and the infectiousness of the infected, number of infected people asymptomatic and number of infected people symptomatic. Okay, so, and it's important that this is a continuous function of time. Okay, so that accounts for going forward in time for the loss of susceptibles due to infection. But there's another loss of susceptibles going forward in time, and that's the loss due to vaccination. So I want to account for transmission change in terms of loss of susceptibles due to vaccination. So I identify a time forward from this TX value when we moved from before the last day of daily reported cases to the next day of daily reported cases. I want to identify, call that TX. I want to go to a time T2, which I'll call March 1st. This was January something, 17.3. I want to go to time March 1st. And well, and as I just described, this is the transmission rate for that time. But from March 1st, time T2 to May 1st, that's 2 months, March and April, March 1st to May 1st, I want to increase the transmission due to what I call the relaxation of social distancing. So what happens? What will happen between now and May 1st? More and more people will be vaccinated. They'll feel more confident about interacting socially, returning to their normal lives. So there will probably be a relaxation, not due to government measures, although possibly even to government measures, but mostly due to just a change in social behavior, because so many people are vaccinated, they feel they can change their behavior. They don't have to stay home all the time. So I increase the transmission in this by multiplying the transmission rate back here by this expression. And so there's a, if T is equal to T0, this is just 1. And it matches the earlier expression. But if T is greater than T0, then this term comes in here to increase transmission. So I assume after May 1st, there's between March 1st and May 1st, there's an increase in transmission due to this relaxation. Again, I go from May 1st to July 1st, I identify time T4, which is July 1st, in which there's a further relaxation of social distancing. And I add another term in here that picks up when T goes later than T3. So it's a further increase in social distancing relaxation. So past, in fact, T4, there's a further decrease in social distancing, and that term goes here. So there's these 3 intervals of time in which social distancing is relaxed, decreased, and the result is an increase in the transmission. So those values, that's all just guesswork, but we could elaborate more on that. Okay, so here's the model, and it's for 3 different efficiency values. So up to January 15th, it's just based on data. Remember, these vertical bars are the daily reported cases data. This red graph here is the model simulation of the daily reported cases data for the case that the efficiency is 90%. And it goes through the daily reported cases rolling average values exactly up to January 15th. But after January 15th, we have a new transmission story, which I just talked about. And vaccination has started back here on January 1st, which is here. And now vaccination starts to remove. We already knew that these number of cases was going down throughout January. And it continues to go down. And because of vaccination, it goes down forward from yesterday, more and more. But then there's a upswing due to this relaxation of social distancing. And it depends on the vaccination efficiency. Red is what? 85%. Green is 90%, and blue is 95%. So blue is the best, of course, because you have the most efficient vaccination implementation going on. And you've vaccinated 59 million people out of however many, I said 68 million people. And the red, you vaccinated 56 million, and the, no, red, you vaccinated 56 million, green, you vaccinated 56 million. But we see the story here of how vaccination affects transmission and the level of the epidemic and the, in fact, this is a success story because by September 1st, the epidemic is just about gone. But there was a price to pay with this efficiency at this lowest level because there was this bump up in July and June, and there were certainly deaths associated with that. And we can modify all the parameters and all the information in this to get different expressions for the effectiveness. But one story to note here is that what's more important, the efficiency of the vaccination or the bump up in social in transmission due to social distancing relaxation? They're both important, but it's most important to get the number of vaccinated people down to a low level. That's most important. But there's a price to pay if you have a lot of deaths in this interval of time here. Okay, I want to show you another model that projects forward. This is based on, how's my time moving? Okay, we're okay. This is based on the IHME. That's the Institute of Health Metrics Evaluation at the University of Washington. Their modeling is very important, very publicized. And here's their graph for what goes on in the UK, starting August 20th and continuing through May 21st. Not as far as I went, but to May. Remember, I went to September 1st. Here was May for me, right in here. And our models are essentially the same. But now what are they graphing? Back here, I'm graphing daily reported cases. They're graphing both daily reported cases and unreported cases. And they assume that there was almost twice as many unreported cases as reported cases. So their graph is higher here. This is both reported and unreported. But when vaccination starts around here in January, of course, this is going down. That's in the data. But then it goes down more sharply with the arrival of the vaccination program. And they have four graphs here, the purple, or I forget what color it is. Maybe I think it's the purple. That's the current projection. If they improve that with universal mask, it would go down to this level here. This is that one, the blue. The red is the worst case when they have relaxation of social distancing and masks are given up and so on. That's the red one. And then if they included the possibility of new variants. It doesn't have much effect though. That's the whatever color that is, blue, I guess. So that's their model. It's similar, but somewhat different. It has and by this, what is their model? It's just what we call an SEIR model. It's a differential equations model, susceptibles, exposed, infected, recovered, but it's extremely complicated, extremely complex with many, many subcompartments, many, many features brought in, many features. So it's a very elaborate, very complex model. Okay, so let's go to the US. I'll skip this a little bit. My time is a little bit short. So this is the background story. As of January 1st, a month ago, we had 20 million total cases, more. It's up to something like 26 million now, I think. And we had a terrible loss of death due to deaths. And so there's some background in that. I won't go into specific details. Now I make the same assumptions that I made for the UK. F is 0.4, new one is 0.4, new 2 is 0.6, 8 is 1/7, new is, I said new, what's the other one? Eta. Okay, those are the same values for the earlier model. And I take the susceptible population to be 331 million people, day 0, which is March 7th. Okay, so here's the data, and it's really terrible. This is the daily reported cases data for the US. This is based on Wikipedia data up through January 15th. This last bump here is the bars January 15th. And we see it's terribly zigzaggy. It'd be terrible to try to use this data. So this is the cumulative data. It's much nicer, as I said, but it's also not quite as informative as the daily reported data. So we average the weekly reported cases data, and we get the purple dots, which are here. They're the dots. You can see dots. And that's our average weekly reported cases data. The vertical bars are, again, the daily case. You see how it jumps around so much everywhere, those vertical bars. And then we take the B-spline cubic interpolation of this daily smooth reported weekly cases data. And that's the blue graph, just like we did for the UK. And it goes right through those dots. Okay, here's the model simulation then based on that input, just as I described for the UK, it's the very same. And we do see this curve all the time in the news. This is the daily reported cases, rolling average weekly data that is presented on the internet all over the place. And this is our model version of that. Okay, this is the cumulative story, just as I mentioned for the UK. And this is the unreported cases, cumulative, given by this formula right here in our model. The blue graph is the reported cases, cumulative, in our model. The dots there, the purple dots, are the data. There's a nice agreement here between the two. The purple graph is the unreported cases at time t, day t, and the red graph is the reported cases. So the model tells us how many cases are asymptomatic on day t, and it tells us how many are reported, unreported, how many are accumulating reported, how many accumulated are unreported. So our model gives us that information. And this is up to the last day of reported data, January 15th. But we want to go past that. We want to go into months ahead and see how vaccination has its impact. So I'll make some assumptions, excuse me, about vaccination, and I'll be brief about this, but we'll assume that vaccination starts February 1st. Of course, it started a month ago, but it wasn't truly effective a month ago. There were not that many vaccinations given a month ago, and they were not truly effective for 3 weeks or before they took effect or before the second dose was given. So we'll just, for simplification, take the date to be February 1st, later than UK, which was more efficient and started earlier. So here are the same equations. We have roughly 1 million people being vaccinated each day going forward from yesterday. And our efficiency will take to be different values F. It's a fraction between 0 and 1. Okay, so just like with the UK, I have to develop my transmission rate going forward. So I'll do it the same way, but I'll take 2 weeks from the last daily cumulative reported cases transmission information, and I'll take the last value here, which is day 317.3, and I'll go forward just as I did, same way with the UK. And again, I'll implement the lessening of the increase of transmission due to social distancing the same way that I did for the UK, but it has different values here and a different story here with different values for the dates and perhaps, and for these parameters in those expressions. I'll just skip over that. And here's the story for the vaccination efficiency varied through 3 values, and the model simulation of what happens up to September 1st. So the last day of reported data is January 15th, right there. We go forward, we start the vaccination program here at 1 million per day times the values of F, which are red 90%, 0.9, blue 0.8, and green 0.7. So red's the best, of course, blue is not as good, green is not nearly as good. So we see that in this situation, the vaccination has not fully brought the epidemic to a very low level, except in the case of this high efficiency, 90%. And so this is the model story for vaccination for the US. Here's the IHME version. They go out to May 21st. There's a similar story. Remember, these are total, both reported and unreported daily cases data. We have the current projection, which is, I think, the blue, the purple. We have the variant, new variant spreading, that's the blue. The green is the best case, universal mass. The rapid variant, the worst case is this red. So it's similar to my story, and the vaccination program is not yet successful in the US, according to this version of the projection for their model. Okay, summarizing very quickly, we've developed a model for COVID-19 based on a standard type of SIR model with its various features, which include asymptomatic infectiousness, which is so important, and the relation to the data, which involves reported symptomatic infectiousness, and also the unreported symptomatic infectious population. We develop a identification for the transmission rate up to the time that the data is available. And that's a story that connects to this daily reported symptomatic infectious population, which they are medically certified to be infected and infectious. And then we applied the vaccination program for the United States and the United Kingdom, and we see how it influences the evolution of the disease. It can be successful, depends on the effectiveness of the vaccination program and the relaxation of social distancing measures. So that's the story that I've put together for you. I'll be happy to answer questions. So please ask questions if you have any questions. And I thank you very much for listening to what I've had to say here. Thank you. Thank you very much.
Thank you very much, Glenn, for the interesting talk, very timely. We do have questions waiting for you. The first one I promised to be allowed to ask a question is Michael Wolfson. Michael, do you want to ask a question directly?
Sure. If you can hear me all right, thank you very
well.
I can hear you very well.
Thank you very much for the talk. My main question is, what do you mean by vaccination effectiveness? The vaccination is considered to have two effects. One is to reduce the severity of any illness once you're infected, and that seems pretty clear. That's what the clinical trials were all about. But the other one, which is still an open question, is whether it reduces the virus shedding. You could be infected, not get very sick, but still infect other people. And it looks to me from your equations, if I understand them, that you're assuming that once you've been vaccinated, you can no longer infect anyone else. Have I understood correctly?
Well, I do not consider deaths or illness in my models. So I'm not measuring the effectiveness of vaccination in the sense that it reduces mortality or morbidity. I'm assuming that the vaccination reduces infectiousness, transmission, and that's an assumption. And percentages are given for Pfizer and Moderna and so on. And they're not perfect, but they're known to be high. They have a high value. Now, recently, the Johnson & Johnson vaccine claimed to be it had a low value of reducing infectiousness, 64% or something like that, but a high, almost perfect value in preventing mortality. But my assumption is that vaccination reduces transmission. And that's important because that's how we can use vaccination to move toward what's called herd immunity. If we can reduce the number of people who are susceptible by vaccination, then we have the chance to bring the disease down to a very low level. So that's my assumption. And the efficiency involves more than just the value that's given by the maker of that vaccine, the 94 point whatever percent that are successfully rendered lacking in ability to transmit the disease. But it also involves, as I said, the second dose to get full effectiveness, but it involves the time period between the moment you receive that shot to the moment that you start to become truly non-transmissible. And so that's what I understand by the efficiency. And it's a value that changes. It actually changes with time. I didn't change it with time, but we could try to bring in more information about the vaccine, the timing, the number of doses, the follow-up, the second dose, and so on. That could all be brought in as further information becomes available. That's what I mean by the efficiency.
Thank you, Glenn. Ping Yan, I'm sure you know him, from the Public Health Agency of Canada. I think he has a document to describe different way and rigorous way of how to count and calculate the efficiencies. I'm not so sure it's the internal report or not, but I'm sure we Ping Yan from PHAC will be able to address some of those issues more rigorously. There are a number of questions waiting on the line, and Amin Fazil and from Public Health Agency of Canada. Maybe Amir, you can ask questions. I know you are on. You are chairing another meeting very soon. Yes. Amir, yeah, please.
Thank you. Thank you for the presentation. I'm just wondering, in your last bullet, you mentioned that I guess relaxation of social distancing comes into play. I don't recall you describing how you actually incorporated relaxing public health measures as time progressed.
Well,
in your model.
The relaxation going forward, I don't have relaxation incorporated before the last day of reported data, because somehow it's buried inside that data. But going forward from that time, January 15th, for example, I have relaxation of social distancing. And what I mean by that is that the transmission rate increases. It increases. Before that day, it just has a form that we identify. But after that day, then social distancing has an effect, and it results in an increase in transmission. So this is the transmission term. It has this formula right here, if you can see my pointer. And from March 1st to May 1st for the UK, it's increased. If that value there, 0.03 were 0, it would exactly match this value up here. But it's bigger than this value here going forward from March 1st, because it has this parameter 0.03 in front of this term right here. So that increases it forward from time T2. And then from time T3, which is May 1st, it's increased even more. It has this term added. So this term is bigger than 1 here. This is even bigger than that term. So there's an increase in transmission in these intervals, March 1st to May 1st, May 1st to July 1st, July 1st to forward to September 1st, in fact. And so there's an increase in transmission, which I connect to a relaxation on the part of people as they get vaccinated. As people are vaccinated, I think they will be more social, they will have more contact with other people, and sometimes their vaccination will not be effective, and they will increase the transmission. I think that's an assumption in the IHME model as well. But that's how I introduce relaxation of social distancing and increasing transmission. It increases transmission according to these changes in the formulation of the transmission term.
Thank you.
Thank you. The next is Kayudi. I hope I pronounced right. Kayudi Alumoyin.
Yes. Thank you very much, Dr. Webb, for your talk. And also thank you for the papers you've published on COVID-19 since summer. I'm a graduate student, a PhD student at Middle Tennessee State University, very close to you.
Okay.
And I've had the opportunity to read your papers, you know, the ones that came on medRxiv and so on. So I have a question. In this, in your talk, you used the daily data, and I think in one of your papers you used cumulative data. So I want to know, do you have graphs for like the vaccine effectiveness when cumulative data is used? Like, do you have that?
Yes, I can produce those graphs. It's the same way I produced these graphs. You take the model, and the model involves the compartments capital R of T and capital U of T. And then we get the cumulative reported cases by just this integration formula, and the cumulative unreported cases by this from the model and these parameters. And so it's possible to develop the cumulative information from the model as well. But as I say, the cumulative information is somehow not as revealing as the daily data, the daily reported rolling average data, which is where it was. That's here. This is the model and the data as well. And somehow this gives more information. We can see, we can understand better that there's a decrease here. We see that there's a change in concavity here. The concavity changes. It's up here, it's down here, it's down here. But this information is more revealing, and it's more important, I think, to use this information, which is very much related to the cumulative data, but it's more difficult to fit. And you can take the cumulative data and just fit it independently of the daily data. Of course, then you just subtract day by day to get the daily data. But that daily data that you get in that way may not match the true daily data rolling average weekly. So there's that issue. And I prefer to work with the daily data, rolling average daily data, and the cubic spline approximation of that.
Thank you, Glenn.
Thank you. Yeah.
So now questions for Mara Lamuz. Mary, want to raise a question directly?
Yes, hi. First, I want to thank you a lot for the talk. I have like two questions. First is, when we consider that the proof is positive, when can we consider it positive? Because it's a continuous, it's not a discrete meaning. What I mean is, for example, in pregnancy, it's obvious when the patient is pregnant or not. We could say, yes, let's say the proof is positive or it is negative. But here, when can we say that the proof is positive? Because if a patient is infected with only one particle, are we going to say that that patient is positive for the proof? Or are we going to say when the patient is infected with more than 1,000 particles or more than 100 particles, or when? Next, this is related with the previous question. When we are doing the proof test, because the proof is not a screening method, besides all the false positive and false negative that the proof can has, also the proof has the false negative that goes very, very high, because this proof is not a screening. So all the people that is not being tested and is infected is going to be like a false negative. So there is no only the false negative and false positive that per se the proof has, instead also the false negative that we generate because we are not screening all the people. And also, besides this, yes, we are talking about a mathematical model, and I think that related to this model is to try to diminish the amount of inoculum that the patient that is going to be infected is going to have. This is, as you are talking about the transmission and all this, yes, the transmission depends on many things. For example, you talk about the time of exposure and how many contacts the patient, well, the susceptible person can has with the infected people. Here, if the person that is susceptible is using, for example, a mask, then the particles that are going to go to the respiratory tract of the of this susceptible person are going to be very fewer than if the person is not using the mask. So in that sense, if we can do that, the people that is going to be infected get infected, but with less particles, is going to be a response, a better response, because it's not going to be all the particles at the same time.
Oh, okay. So I understand that you're asking about very many important issues that can be incorporated into a model. Now, the model I've presented is very simple. It's very simplified. And the goal was to develop a simplified model that could be understood, could be explained completely, and could be informative. And it's in contrast to a very complex model that would involve features, as you mentioned, like the number of contacts an individual might have and who's infected, and the false negative and false positive test results, and other issues, the level of infectiousness depending on time since infection and the age of the person who is infected or susceptible. So many complex issues can be brought in, but they complicate the model tremendously, and they require elaborate parameterization to account for. So what I want to do is take the data, which is, as I talked about, it's a mess. It's very zigzaggy. It's the daily reported cases. That's the data. But those cases are medically confirmed, by the way. It's not some guesswork. They have to be certified in some sense. It varies from location to location. But there are false reports, of course. But for the most part, they're somewhat reliable. But they're only a fraction of the cases because more than half are unreported. So there's a tremendous problem in connecting data to a model and in connecting features that you want to build into a COVID epidemic into a model. I tried to go simple so that it can be explained, but still have meaning. And all the various parameters that I have chosen can be modified and varied to see what happens when we change those parameters. And the model can certainly be complexified. We could introduce age classes in the susceptible population or the infected population. That's very important. We can do locations. We could have different results and different data in different locations. We can have so many complications. I think the IHME, even in some of their examples, they had altitude of the location. That was considered to be some feature that could be examined. So we can make models very complex, still very valuable, very useful for predictions, for understanding. But I'm on the other side. I'm trying to introduce a very simplified model and still give meaning to the work of the model and the value in predicting forward. Thank you for the questions. It's a good point. Very good points.
Thank you very much. Can we write you by email? We want to share an article that we published with my sister twin that is going to ask the next question. And I published an article in the International Journal of Biology and Medicine about COVID-19 pandemic, and we wanted to share it with you. Can we write you by email?
Absolutely. Please do. I absolutely welcome that. I appreciate it very much. Absolutely. Thank you.
Thank you, Mara. And there are other questions, but I think we have to conclude because a certain portion of the audience are supposed to switch to another expert panel discussions with the Canadian Public Health Agency of Canada. On behalf of the Fields Institute and on behalf of the National Task Force, I want to thank you, Glenn, for this very interesting and very timely lecture. So we are looking forward to see your papers. And
okay.
Thank you again, please.
Okay, thank you all very much. And I wish everyone very well, stay safe, stay strong, be careful. And I thank you very much for your attention.
Thank you.
Thank you.